Hi and welcome to Gaffy's Grinds. This is video 4 on our series on thermochemistry. If you're new to the channel, you're very welcome. And if you're not new to the channel, welcome back. A couple of the usual reminders. Try and eliminate any distractions before we begin. That's so that we do not overload our working memories. And if you want to know more about working memory and why we shouldn't overload it, you should go and watch our video on the channel that talks about how we learn, and it explains a little bit about why we do things this way on this channel. We don't want to overload our working memories because it stops us from learning things. So try and eliminate any distractions by turning off your phone or putting it in another room unless you're using it to watch this. Put it on do not disturb or something that's going to stop notifications coming in. And also the main thing when you're watching these videos is that when I'm explaining something, you should be listening, not copying down anything. Just listen, try and understand what I'm saying, and break down the ideas really small. You listen, explain, and then we do some practice. If I need you to write something down, if I need you to do some practice, I will ask you to. It's really important that you do any of the tasks I ask you to do. It's really important that you do them. If you don't put pen to paper, you're wasting your time watching the videos. Okay, so we're going to get started here. We're going to be looking at different types of heat changes that can happen during a chemical reaction. And I've got to give you a quick warning. This video is going to be quite heavy on definitions. This particular section in our Leaving Cert Chemistry topic is quite definition heavy, but I don't want to just give you the blank definitions to say, hey, go off, you go and learn them. I will try and explain them as best as I can, because chemistry is about understanding what's going on and loving understanding what's going on, not just learning off definitions. So here we go. Quick reminder, this now you can look at the screen. This is just a general overview of any chemical reaction. Chemical reaction involves reactants turning into products. Reactants we always see on the left-hand side of the arrow, products we always see on the right-hand side of the arrow. And this is just a general reaction, what's going on here. The colored shapes represent atoms, okay? And obviously the before and the after, I want you to study them there for a second, just have a look at them. What's happened? And this is what happens during a chemical reaction, atoms change positions. Now, I can't just magically do that. For that to happen, we need to break bonds. Okay, so these lines represent chemical bonds, and bonds need to break. So if you want a reaction to happen, you need to break bonds. So bonds need to break. Okay, now this obviously is going to require energy. Requires energy. How does the substance that's getting the bonds broken get that energy? Well, it usually gets it in the form of heat. So here I am drawing a heat source. Ooh, that didn't work very good. Yeah, a heat source. So this just represents a flame. And it's showing some kind of heat source in the surroundings. And these arrows show that the energy is flowing in to the substance. So the energy gets in from the surroundings. That means that this process takes in heat. So we've got a rule here. We've got a rule, and that's bond breaking. Always takes in energy from the surroundings. How much energy? That's a good question. And it depends on the substance, basically the atoms and the bond between them. Depends what type of atoms we're talking about and what type of bonds we're talking about. In between them, it's going to be a different amount of energy for different substances. So different atoms chemically bonded to other atoms going to have different amounts of energy. And from that, we're going to get our first. So we're going to, if we talk about the energy required to break a particular bond and separate the atoms, because that's what has to happen if a chemical reaction is going to occur. So the amount of energy required to break a bond, so up here, required to break this bond, and depending on the atoms, it could be a different amount of energy, but whatever the amount of energy that is required to do that and separate the atoms to allow them to react, we call this the bond energy. So different bonds will have different energies. Okay, so this is the bond energy. This is going to be your first definition. So I suggest now that you pause the video and make a note of that. That's important. Pause the video now and do that. Okay, so you should be watching now if you have done that. Now, that gives us this idea that bond breaking, when we're breaking bonds, it's always endothermic. It takes in heat. So bond breaking is always an endothermic process. That should make sense to you because you should have watched the previous videos. You should know what endothermic means. What does endothermic mean? 1, 2, 3, speak your answer to the screen. Now, I'm hoping you said that endothermic means the reaction takes energy in from the surroundings, or energy is transferred in to the system from the surroundings. Well done if you said that. Now, let's go back up and review what's after happening after we break the bond. So after the bond energy has been given in, enough energy to break the bonds, we then have these atoms that were in the reactants, but they're separated from each other. So there's the blue square, the green triangle, and the 2 red circles. Noticing that they are now separated, no bonds between them. And that means they are free to move. We're going to show that using, we're going to show that using these movement lines. So these movement lines show that these are moving around. And when they are moving around, they are free to collide with each other. And if they collide with enough energy, so collide just means crash into each other. Collide with enough energy. What is that amount of energy? There's a name on that amount of energy that needs to be reached for a reaction to start. We learned it in the last video. What's the name for the amount of energy needed to start a reaction, or needed for a reaction to occur? What's the name for that? 1, 2, 3, speak your answer now. Okay, I hope that you said activation energy. Well done if you got that right. It shows that you're learning stuff for the long term. The activation energy is the minimum amount of energy required for a reaction to occur. So if they collide with the activation energy, then new bonds can form. Now again, bond energy will be involved. The amount of energy required to break the bonds, well, there'll also be an amount of energy required to make, released when you make the bonds. Okay, so when new bonds are formed, this always releases energy. So making bonds releases energy. Now, where does the energy get released to? Where do you think that's going to be? On 3, speak your answer. 1, 2, 3. I'm hoping you said energy gets released. Well, there's only one other place. If it's not in the chemicals, we say it's into the surroundings. So it's either in the system or the surroundings. That's where the energy is. It flows between the system and the surroundings. So how much energy is released? Well, that's going to depend on what type of bond is being made. The atoms that are being joined and the bond that's being made between them. It's going to be a different amount for different substances or different bonds. And it's going to be the bond energy again. So believe it or not, when we break a bond, if I was to take, just as a side, if I was to take this substance here, if I was to break the atoms apart, break the bond, and there were 2 loose atoms, I would have had to put an energy amount in that would have been equal to its bond energy. I would have had to put enough energy in to break the bond. Now, let's say there's nothing else for it to combine with, and it decides, no good, I'm going to stick back together and bond again with the same atom. Well, it's the same two atoms. It had to take in energy. How much energy did it take in to do this? Oh, sorry, how much, when they joined together, scrap that. We took in energy to break the bond. The two atoms are separate, and then they're going to join back together. That's going to release energy, remember? New bonds form, releases energy. So when they form, well, how much energy is going to be released? It's going to be released. It's the exact same amount that you had to put in to break them. So same amount. This is an important idea for later on when we do some calculations. So if we break bonds and then we form the same bond back, it's the same amount of energy, okay? So I'm just going to get rid of that. We'll come back to that, revisit that idea later on. So obviously, new bonds formed releases energy into the surroundings, and that gives us another rule. Bond making releases, or always, I should say, always releases energy into the surroundings. Now, if it always releases energy into the surroundings, what type of process is this? Bond forming, what type of process is it? Okay, I'm hoping that you said bond making or bond forming is an exothermic process. Exothermic process. So bond making is exothermic. Okay, so that's just a quick overview of energy changes in chemical reactions. Why is it important? Well, it's important because we need to consider what happens for the whole reaction. We've talked about bond energy being the reaction, the amount of energy to break one bond or to form one new bond. But there's loads of bonds being broken in a chemical reaction, not just one. Okay, so in this case, this is quite simple. There's just two reactants and each one has only one bond. So you're just breaking two bonds. But we know molecules can be massive. Organic molecules we've looked at before, C20H42. So that's a massive amount of bonds. Between every carbon and hydrogen, there's a bond. So that's a hell of a lot of bonds. And all of those get broken when you, for example, burn it. So if we take a look, for example, at a chemical reaction. So that was just a general one. We're actually going to look at a real chemical reaction now. If we take or consider this reaction, so take carbon and react it with hydrogen, H2. And you get CH4. Now, have a look at that. There's something wrong with that reaction. It's not balanced. So have a look at that and see, can you balance it mentally in your head right now? So do that for me. 1, 2, 3. What do I need to do to balance it? I'm hoping that you can identify that the hydrogens are not balanced. If you couldn't see that, I'm after telling you, go and tell me how you would balance the hydrogens. Okay, right. To balance the hydrogens, we've got to stick a 2 here. That's it balanced, okay? Now, when we talk about carbon reacting with hydrogen to form CH4 or methane, we would often see this symbol after it, delta H. Delta H. This shouldn't be new for us. What does delta H mean? From our previous lessons, speak to that answer to the screen now. 1, 2, 3. Delta H means change in heat or change in heat energy. So the delta H for this overall reaction. Remember, up here we have bond breaking and bond making going on. The question is, well, which is there more of? Which is there more energy given out or is there more energy taken in? And this should link back to your previous video when we looked at reaction profiles. Overall, is the reaction exothermic or endothermic? We know there's bond breaking and bond making going on, but overall, which one is winning out? Which one is there more energy going in or more energy going out? Well, the delta H for this particular reaction is minus 75 kilojoules per mole, which means for every mole reactants reacting here, you're going to produce minus 75 kilojoules of energy. Now this is a chemical reaction, and it gives us our first definition here. This is just a general reaction. I haven't said what type of reaction it is. It's just a general reaction at the moment. So if I want to know what is this guy, the overall change in temperature for the whole reaction, that's what we're talking about here. So we're talking about the energy change when a reaction occurs according to this equation. So this equation is telling us what's happening, is telling us the ratios and the molar quantities involved. We know there's 1 mole of carbon reacts with 2 moles of hydrogen to give us 1 mole of CH4. Again, that should not be brand new stuff for you. We've done balancing equations. I'm hoping you're not jumping in on this as your first topic. 1 mole of carbon with 2 moles of hydrogen gives you 1 mole of methane. That's what the reaction tells us. So it's the energy change when a reaction occurs in the molar quantities in the chemical equation. That's what this guy says here. That's what that is. It's the energy change when the reaction occurs like it says here. Now, if I was to say, okay, well, we didn't have 1 carbon. We started with 2 carbons. What would that do to the rest of the equation? Okay, so tell me what that would do to the rest of the equation. Now, please, 1, 2, 3, speak your answer to the screen. I'm hoping that you know, well, that would change this to a 4 and this to a 2. So we've doubled everything. Now, if you've doubled the molar quantities in the equation, you also have to double the amount of the energy change. So that would go from minus 75 to minus 150. So if you double everything in the equation, you have to double the energy. Simple as that. So what we're talking about is the energy change when the reaction occurs according to the molar quantities in the equation. So that was the equation, and that's the amount of, and this is the amount of energy that's released. We call this definition, or this amount of energy, we just call this the heat, because it's an energy, heat of reaction. We haven't said what type of reaction there is. We know there's lots of different types of reactions, combustions, neutralizations. This is just for any general reaction. When you take the reaction and it happens as it says in the equation, there's an amount of heat, and you can measure this amount of heat. And in the next video, we're going to talk about how do you measure the amount of heat in a particular reaction? How do you measure that energy change? There is a way you can do that. So there's a definition again for us. That is probably a good idea to make a note of that. That's your second definition for today. Let's just have a very brief look at another heat of reaction. We could have 2H2. So if we take hydrogen gas and we react it with water, O2, and the reaction happens to make 2H2O. Well, again, a delta H value for this has been measured, and it's been found to be, the heat of reaction for this particular reaction has been found to be minus 576 kilojoules per mole. Now, again, what I'd like you to do is I'd like you to tell me what the energy change would be if I did this. If I, instead of using 2, I used H2 plus a half O2 to give you H2O. What would the energy change be if I did that, please? Tell me now. So work it out, pause the video and work it out. Okay, you should be watching the video now. If you have tried to do that, pause the video and try to do it. Well, hopefully you can see that we've halved everything in the equation, which means we would have to half the delta H. So delta H equals minus half of that. I think that's minus 288 kilojoules per mole minus 1. Now that is not the heat of reaction though, because that's not what the reaction said. The reaction, the equation we were given, was this one. Sorry, that should be a G, that should be a G, and that's obviously an L. They're just state symbols, doesn't matter. What's important is that that's the equation we were given, and that's the heat of reaction we were given. Okay, so that's our first definition, heat of reaction there. Heat of reaction is the energy change when a reaction occurs in the molar quantities in the chemical equation. So that is our heat of reaction, general definition. As a follow-on, we're going to look at some specific types of reaction now. So that was a general definition for heat of reaction. The next thing we're going to look at is we're going to look at something like this. Say we have a compound. What is a compound? So on 3, speak your answer to the screen. A compound. 1, 2, 3. Okay, a compound, this is what you should have said. A compound is a substance made up of 2 or more elements which are chemically combined. So 2 or more elements which are chemically combined. Different types of atoms chemically combined. Okay, that's what a compound is. So different types of atoms. Say we have magnesium and we're bonding it with oxygen. This is a compound because it's got a magnesium and an oxygen atom and they're chemically combined. So it's a compound. Now, say we wanted to make magnesium oxide. What would we need to do? Well, we would need to make it from its elements. We would need its elements and we would need to form it, form magnesium oxide. So to form magnesium oxide from its elements, we would take magnesium, Mg, and we would add to it oxygen, O2. Now, generally, when we balance equations, we don't like to have half of something. We generally don't like to do this. This is how you could balance this equation, half of O2. Now it will be balanced. Mg, 1 Mg, okay, half an O2 gives you MgO. Again, I'm assuming you know how to balance equations. If you don't, you need to go back and watch the video on balancing equations. I'm assuming that you do. So magnesium plus half an oxygen gives you magnesium oxide like this. This is a balanced equation. Now, generally, I would tell my students to get rid of the half. We don't like dealing in halves. And we would say, okay, so how do we get rid of the half? We would multiply across by 2. Multiply everything by 2. That would give me 2 Mg. Then I could multiply the half by 2, which would give me 1. And I could then obviously have to multiply this by 2 as well. Now, the problem with this is when we are talking about the formation of a compound, we want to deal only in making 1 mole of the compound. So we just want to make 1 mole of the compound. We want to always ensure that whatever we're forming, we are forming 1 mole of it and adjust the equation of the rest of the stuff to make sure that that is true. So say we take this reaction. When we do this, we get Mg plus a half O2 gives you MgO. And it's found that the delta H for this, the energy change, when we do this reaction, delta H is equal to minus 602 kilojoules per mole. This is a very specific type of reaction we're talking about here. We're talking about the formation of a compound, the formation of a compound. So if we were to define what we're doing here, we would say we're talking about the energy change when 1 mole, and this is key here, 1 mole of a compound is formed from its elements. That's how you make a compound. You join its elements together. We're talking about forming the energy change when we make 1 mole of it, okay? And we give this name, we give this particular amount of energy, we call it the heat. Sorry. We call this the heat of formation, because we're specifically talking about the formation of a new compound. So the heat of formation is the energy change when 1 mole of a compound is formed from its elements. So that is another definition, and this is an example. This here is an example of forming 1 mole of a compound. So I'm going to get you to pause it and make note of that definition and maybe that example. Okay, so you should only be watching the video if you've made a note of that. Okay, time to just look at another one now. Okay, so what if we take, for example, H2? We'll start with what we're actually forming. We're forming water, H2O. So when you're writing these, you always want to start with what you're forming. So we're forming water and we're forming 1 mole of water. That's really important. I'm making sure I'm dealing in 1 mole. I'm not going to change the number in front of the H2O because I want to make sure it's 1. So everything else I'm going to adjust. Well, how do I form 1 mole of water? Well, I need to, the elements in water are hydrogen, and hydrogen is a diatom, it exists as H2, and the other element is oxygen, which is O2. Sorry, they're not in the right line there at all. That's going to annoy me, so I'm going to fix it. Sorry. So we've got H2 plus O2. So H2 plus O2 gives you H2O. All right, so that's how you would write that. And then you balance the equation. So it's not balanced right now. So tell me what would I have to do to balance it? Have a quick look. Pause the video if you need to. All right, so hopefully enough time. If you didn't have enough time, pause it now because I'm going to say the answer. Okay, so to figure out, to balance this, you would need to put a half here. So H2 plus a half O2 gives you H2O. And it's found experimentally that the delta H for this, delta H is equal to minus 286. Quick bit of revision for you. Is this endothermic or exothermic? Speak your answer out loud now. 1, 2, 3. I'm hoping that you said this is exothermic. How do we know? Well, we know because the sign is negative, and exothermic reactions have a negative heat change. Now, one important thing to note about this definition is it's the energy change when 1 mole of a compound is formed. That means if we take something like Cu, copper, and we break up the copper atoms and then they just join back together as Cu, will there be a delta H? Well, this goes back to what I was saying earlier. If you have something which is made of, say, more than 1 atom, so say here the copper is made up, it's not like this, but we're just going to imagine it is. Say the copper is made of 3 atoms. That's not technically correct, but I just want to use it as an example, okay? Copper is made of 3 atoms. We say that atoms break up, the bonds break, energy in, remember, to break the bonds. So we've got our 3 separate atoms, and then we form the same element back. So we form our copper again. So this time bonds, new bonds are made, and we form the same thing back again. So say that happens. Well, energy goes in here and energy goes out here. Now, because it's the same bonds being broken and the same bonds being made, it's the exact same amount of energy. So overall, there was energy put in, there was energy taken out, but they cancel each other out. So 0 joules, 0 kilojoules per mole. So when you form an element, there's no heat of formation here. So when you form an element, there's no heat of formation. So same if we took H2, for example, and we formed H2, we formed an element from itself. Is there going to be any heat change? No, there isn't. 0 kilojoules per mole. So that's an important distinction to make right now. Okay, so one important, I suppose the really important thing to remember when we're doing these is that we always have to form 1 mole of the product. So let's do, we're going to practice writing a few of these. So what I want us to do is I want to practice writing equations to show formations of compounds. So I'm going to do one with you, then I'm going to set you up to do a few for yourself. Okay, so let's go. Let's start with this one. Okay, so we're going to do magnesium chloride. So making magnesium chloride, let's make it. So magnesium chloride has the formula MgCl2. So I'm forming magnesium chloride. So there's nothing else here. I'm just forming it. So the arrow is going into, if I'm forming it, it's a product. So it's going to be on the right. First of all, that's the first thing I do. Put it on the right. Draw the arrow showing it being made and make sure it's a 1 because I'm making 1 mole of it. Okay. Now, its elements. What elements are in here? Well, I know I've got one magnesium and I've got 2 chlorines if I was to draw these out. That's what my formula tells me. Magnesium and 2 chlorines, MgCl2. Well, that's going to tell me I'm going to need Mg over here is the first element plus Cl, and Cl exists as Cl2. It's chlorine, it's a diatom. So Mg plus Cl2 gives you MgCl2. After that, then you do any balancing if you need to do it. Now, luckily, in this one, we don't need to balance it. Now, we don't know what the heat change is, but there is going to be a delta H here, and that would be our heat of formation. I'm not sure exactly what that number is. We don't really need to know that right now. We're just practicing writing out formation equations. Okay, let's try another one. I'll do another one with you now. So say we want to form C2. We want to form ethanol. So ethanol, C2H5OH. Okay, so again, I'm putting it as a product because I am forming it. I always form products. So products on the right. It's a 1 because I'm forming 1 mole of it because it's a heat of formation. I'm forming it 1 mole. So what are the elements? Well, I've got carbon, which is just C. What else have I got in here? I've got hydrogen, which is H2. And I've got oxygen, which is O2. Okay, so they are my 3 elements that are in here. I've got carbons, hydrogens, and oxygens. So after that, then we balance it. Okay, so what's not right? Well, first of all, there are 2 carbons here, and there's only 1 here. Now, can I just do that? On 3, say yes or no. 1, 2, 3. Okay, so no, I cannot do that. This is not allowed because that would tell me that this in the beginning is C2 when that's not the way it is. It's really just carbon. So what I should really have is carbon and another carbon that's separate. And I show that by putting a big 2 in front. But again, you guys should know that from practicing balancing equations, which we've done. So 2 carbons. Now, altogether, I have 5 and another 1 here, which is 6 hydrogens. So to balance that on this side, I've got 2 here. So if I make 3 times 2, that's 6. So 2 carbons plus 3 hydrogens. And then here I've got 1 oxygen. Here I've got 2. So how can I fix that? I can do that by putting a half here. So 2C plus 3H2 plus half O2 gives you C2H5OH. And that is how I would write the formation equation for that particular compound. And again, there would be a delta H, and we don't know whether it's positive or negative right now. You would always be supplied that information in the exam. All right, here's a few for you guys to try. I want you to do these ones. NH3, CH3Br, Na2O, C4H10, and Al2O3. All right, so I want you to pause the video and I want you to try and write heats of formation for those 5 things. Do that now. Okay, so you should only be watching the video if you have tried to do heats of formation reactions for each of these. This is what you should have. For NH3, ammonia, we should have NH3 as the product. We're forming it. And it should, the elements it's formed from is N2 plus H2, nitrogen and hydrogen. To balance it, we need to do a half N2 and we need to do 1.5 H2. That's a bit awkward. The reason why it has to be awkward is because we have to have only 1 mole over here. So we have to keep that as 1 mole. Remember, that's the key rule here in heat of formation. The reason why it has to be 1 mole is look at the equation. The heat of formation when 1 mole of a compound is formed from its elements. So it has to be 1 mole. Right, the next one, this is what you should have. CH3Br is the compound being formed. The elements here are carbon plus hydrogen plus bromine, which is Br2. If you didn't know it was Br2, you do now. Go and fix it. Pause the video now. Okay, hoping now that you got this. So the carbons are balanced. So 1 carbon, 1 carbon. So tick and tick, they're done. The hydrogens, I've got 3 carbon hydrogens here and only 2 here. So if I do 1.5 here, I will make that balanced. 1.5. The bromine, I've got 2 here and I've got 1 here. So if I half this, then it will be balanced. So I've got carbon plus 1.5 hydrogens plus 1.5 bromines. Plus a half a bromine gives you CH3Br. Again, that's quite challenging. So well done if you got that right. Next one, I'm forming the compound Na2O, sodium oxide. The elements are sodium, Na, and oxygen, O2. So Na plus O2. Now, is it balanced? At the moment, it is not balanced because I have 2 sodiums here and I've only got 1 here. So I put a 2 here, that balances it. And I've got 1 oxygen here and I've only got 2 here. I've got 2 here, so I need to half that. So 2 Na plus a half O2 gives you Na2O. Well done if you got that right. If you didn't get those right, guys, and you think you're getting the hang of this now, pause the video and do the next 2. Try and fix them before I do them. Okay, so you should be watching now. If you're confident you've got the last 2 correct. So here's the compound. We're forming 1 mole of C4H10. Okay, its elements are carbon plus hydrogen. So C plus H2. And to balance it, we're going to need 4 carbons and we're going to need 5 H2s. Well done. That one's a bit easier, I think. And the last one, the compound we're forming is aluminium Al2O3. We're forming 1 mole of that, Al2O3. So the elements are aluminium plus oxygen O2. To balance this, we're going to need 2 aluminiums and we're going to need 1.5 O2s. Or 1.5 O2s. Guys, well done if you got those right. Those were quite challenging, but it's a key skill being able to write heat of formation equations. It's going to be really important for future calculations, which is what really comes up on the exam paper. So again, we're building it up skill by skill. We're not going to jump straight into doing the hard calculations on the exam paper, building it up skill, 1 skill at a time. We're going to take a look at another reaction now, another type of reaction. So remember that was a heat of formation. Those were formation reactions, forming 1 product. What about a second type of reaction? A reaction we're probably more familiar with, where if we take, for example, if we're in school and we're using a Bunsen burner and we've got our gas taps now. Trying to draw these gas taps. How do they look? We've got, okay, we've got this and we've got a switch on top that we can control. And we've got, this is a gas tap. Now we can hook up a hose to here, but basically out of here will flow a gas. And if we give it a source of ignition, like a match or a lighter, we can burn this gas. We can start a fire, we can use it as a Bunsen burner. So this gas is flammable, can be used as a fuel. What is the gas that's in there? Well, it's this substance called methane. So methane. And Why does methane burn like this? Well, methane burns when we mix it with oxygen. And we always produce the same two products when we burn a carbon-based fuel in oxygen, and those products are always carbon dioxide and water. So carbon dioxide and water. We call these types of reactions combustion reactions. This is a combustion reaction. So this is what we're going to be talking about next, the heat change when a combustion reaction occurs. All right, so if we take specifically this particular reaction here, and we take methane, which is CH4, and we combine it with oxygen, and we produce CO2 plus H2O. The delta H for this reaction is, as you would expect, a negative number. Why is it negative? What does this mean? Negative delta H. What does that mean? Speak your answer to the screen on 3. 1, 2, 3. It means that the reaction is exothermic, which makes sense because we use them to heat things up. So we release, when they burn, they release heat to the surroundings, and that allows their surroundings to be heated up. And it has quite a high number when we burn methane, 890 kilojoules per mole. That's why they're useful, because they release a lot of energy. Now, this is not a balanced equation at the moment. So what I want you to do is I want you to pause the video and I want you to write it down and practice balancing it. Okay, so what you should have done, and you should only be watching this now if you have balanced it. The only thing we need to do to get it to balance, and I hope that you spotted this, is we need to put a 2 in front of the O2. Again, if you're not sure on balancing equations, guys, you need to go watch the video on balancing equations. Okay, I'll try and put a link in this video when I can. Right, so this is a particular type of combustion, a particular type of reaction that we call a combustion reaction. Now you will notice that this here is for 1 mole of the thing that we're burning. So the methane is what we're burning. We're talking about 1 mole of it. So when we use 1 mole of a fuel and we burn it in oxygen, and usually we need excess oxygen, which means there's loads of it, there's more than you need. We take 1 mole of a fuel, burn it in excess oxygen. We always produce CO2 and H2O in a combustion reaction. So what about the energy change then? This guy here. Well, this is for methane, but the energy change when 1 mole of a substance is completely burned in excess oxygen. This means that there's more than enough to get all of the fuel to burn. Okay, so excess is the energy change when 1 mole of a substance is completely burned. Here's your 1 mole of a substance. In excess oxygen, you've got lots of the oxygen. There's an energy change, this energy change that we showed over here. What is the general name for this then? We call this, oops, apologies about this now. We call this the heat of combustion. Combustion because that's the type of reaction we're doing. So it's different from the heat of formation. We're not just talking about forming 1 mole of a product anymore. We're combusting a fuel. So it's a combustion reaction. We're mixing it, a fuel with oxygen. Okay, so that's what we mean by heat of combustion. So a good idea now, if you take a note of that, write down heat of combustion as a definition. You know that what that means. It comes up. You have to learn it, guys. But I hope that you understand what it means now. Also, it's a good idea to maybe take these down as an example of combustion reactions. Okay, what I'm going to do now is we're going to practice writing down some equations for combustion reactions of different substances. Okay, so, and remember, we're always going to be combusting 1 mole. So let's start with let's start with this one. We've got C2H6. Okay, so we're going to combust this now. C2H6. That's all we know. We want to combust C2H6. What do we have to do? Well, I know I have to add oxygen. So plus O2, that's the first thing I'm going to do. That's the other reactant. And I'm going to produce, so I'm going to draw my arrow and I'm going to talk about the products. I'm always going to produce the same two substances, and you guys need to know this. You're going to produce CO2 plus H2O because it's a combustion. And this is going to have a delta H equal to, I'm not sure what exactly yet, but we don't know the exact number for this, but I might be able to tell you in a minute. Right, so C2H6 plus O2. The next thing we need to do is see is it balanced. So straight away, I'm looking at my carbons. 2 carbons here and only 1 here. So I'll put a 2 here to balance that. Let's check the hydrogens next. I've got 6 hydrogens here and I've only got 2 here. So what I'm going to do is put a 3 here to balance that. Okay. Check my oxygens. Finally, I've got 2 times 2 here, which is 4 oxygens, and I've got 3 times 1 here, which is 3 more. So 4 plus 3 is 7 oxygens. So I've only got 2 here. So how do I make this into or to balance it? I would put a 3.5 here or a 3.5. 3.5 or 3.5. Now that is balanced and it is what I want. This would also be balanced, guys. Again, sometimes when we're writing equations and we're not talking about heats of reaction, we would often do this, where I double everything like this. C2, 2 C2H6 plus 7 O2 gives you 4 CO2s plus 6 H2Os. That is also a balanced equation. All the atoms will be accounted for on the left and the right. It's balanced, but it's not balanced to show me a heat of combustion because I'm burning 2 moles of the fuel now, and that's not what I want. Look at my definition. The energy change when 1 mole of a substance is completely burned. So that's why this one would not be correct here. This is not correct. Now the delta H for this particular reaction is minus 1561 kJ mole minus 1. Okay. Right, I'm going to do another one now. Okay, so I'm going to do another one and then I'm going to get you guys to do a few. Okay, so let's look at this one, H2. We're going to burn H2, hydrogen. Right, so what do I have to do? If I'm combusting hydrogen, I need to combine it with O2, oxygen. Okay, now in this case, you have to be careful about the products. Look at it and see, well, what could I actually possibly form here? All right, well, I'm hoping that you can see there's no carbon. It's not a carbon fuel. So there's not going to be any carbon dioxide as a product here. And we learned about this when we talked about using hydrogen as a fuel before in a previous video. We learned that that was one of the benefits. Why do scientists want to create hydrogen as a fuel for cars, for example? It's because they don't produce carbon dioxide. They don't pollute and they don't release carbon dioxide. So it could save us on our carbon emissions. All it produces is H2O, water. All right, so now that you know that, try and balance that equation there in your head for me. What will I need to do? Okay, I'm hoping that you see that we're going to need to half the oxygen here. So half the O2, and that would be balanced. You could have also done this, 2H2 and 2H2O. That would also be balanced, but it doesn't give us a balancing for the heat of combustion because that would be 2 moles of hydrogen. And we don't want that. We want to know 1 mole of hydrogen. So technically, we want H2 plus a half O2 to give you H2O. All right. I want you guys to do these ones for me now. Okay. So I want you to burn these substances for me. C3H6, try that one. C4H10. Beryllium, Be. C2H5OH. All right, that'll do. So try those 4 for me and then pause the video. Pause the video while you do them, please. Okay, so you should only be watching the video if you are now doing heats of combustion for those 4 heats of combustion reactions. Okay, so this is what you should have now. You should have done this for the first one, C3H6. You should have combined it with oxygen as the other reactant, O2. And you should have produced CO2 plus H2O because it's a carbon-based fuel. All right, then you need to balance it. So it's not balanced at the moment. So there's 3 carbons here. You need 3 here. There are 6 hydrogens here, and there are only 2 here. So this needs to be a 3. And then there are 3 times 2, which is 6. And there are 3 times 1, which is another 3. That's 9. So this will be 4.5 O2s. So C3H6 plus 4.5 O2 gives you 3 CO2 plus 3 H2O. And with a delta H equal to question mark here. All right, next one. C4H10 plus O2 gives you, okay, so you've got C4H10 plus O2 gives you CO2 plus H2O. To balance that then, you're going to need 4 carbons here, 4 in front of the carbon here. You're going to need 5 in front of the hydrogen there, and you're going to need 6.5 in front of the O2. All right, so well done if you did that. Next one is a little bit trickier. We've got Be plus O2. Be plus O2, again, you're always combusting an oxygen. So the products are going to be different this time. There's no carbon here, so there can't be carbon dioxide in the product. So what is the product going to be? Well, it's going to be BeO2, beryllium oxide. Okay, so beryllium oxide. So well done. If you got that, that's already balanced for you. So you don't need to change anything. So it's just BeO2. And that's, again, going to have a delta H with some number, and it's either going to be exothermic or endothermic. Now, it's not either going to be, sorry, that's an important point to make, that because they're combustion reactions, all combustion reactions, when we burn things, always produce heat energy. So it's always going to be a delta H, which is negative for a combustion reaction. Right, let's try the last one here. You should have C2H5OH plus O2 gives you CO2 plus H2O. All right, so let's balance this now. We've got 2 carbons here. We've got, sorry, I'll just do it in red. 2 carbons here. We've got 2 carbons here now. 2 times 1, remember, is 2. We've got 5 and 1 here is 6 altogether. So over here we've got 2, so we're going to make this a 3. And then over here we've got 2 times 2 is 4, and 3 times 1 is 7 oxygens. Over this side we've got 1 oxygen here, so be careful about that. And then we've got 2 here. So we've got 1 and we need 6 more. So here's 2. If I make this a 3, I now have 6 oxygens plus the 1 here, which is 7, and I've got 7 over here as well on the right. So that would be now balanced. So that is how we would write equations for combustion equations, basically. Again, this is going to be a really important skill when we go to do the longer calculations. All right, so we've got one summary question here to sum up what we've actually had a look at here today. So what I'm going to get you guys to do is I'm going to get you to just do question 1A first of all. So have a go at question 1A, just quick little bit of guidance here. You just have 3 chemical reactions and you're asked in part A to give one reason why all 3 are classified as examples of combustion. So write down what you think the answer is to that now. Pause the video, write it down. Okay, so you should only be watching if you've written the answer to question 1A. They're all combustion reactions because they all involve burning a substance in excess oxygen, or they all involve burning a substance in oxygen. That's the key thing to a combustion. It's burning in oxygen. So that's why they're all classified as examples of combustion. Let's have a look at 2B, 1B now. In terms of energy changes, what type of reactions are all of these? So in terms of energy changes, so look at the energy change. So the energy change, when you're answering something like this, the energy change is found over here. Remember, energy change is delta H. Delta H, okay? So in terms of the energy changes, what type of reactions are they? So pause the video and write it down. Okay, I'm hoping that you realize that they are all exothermic because they all have a negative sign. They are all exothermic. Well done if you got that right. Part C, only reaction 1 represents a heat of formation. Give reasons why 2 and 3 do not. Okay, so pause the video now and write that down. Okay. Number 3, I'm guessing you would have definitely got. So I'm going to do number 3 first. Why is question 3 not a heat of formation? Oh, sorry. Yeah, why is number 3 not a heat of formation? Heat of reaction 3 is not a heat of formation for this reason. You are forming 2 moles of the compound water. You're forming 2 moles of water. So it's not a heat of formation. A heat of formation is when we form 1 mole. So well done if you did that. Hope you did spot it. What's wrong with number 2? Well, what's wrong with number 2 is you are forming, obviously, 2 moles of water. So there's a problem. But you're also forming 2 compounds. So it's not a heat of formation because the heat change here, we're forming 2 compounds. So we don't know if that heat energy, it's for the 2 compounds. So you can't call it a heat of formation. All right, so well done if you did get that right. The last bit, you needed to refer back to the previous video, draw an energy reaction profile for reaction 3. Now, I'm just going to really quickly sketch this here now. I'm not going to use the ruler or anything. This is what you should have. You guys should have used the ruler like I showed you nice and neat in the last video. You should have, well, it's an exothermic reaction. That means that the reactants have more energy than the products, like that. Okay, so this is products. And this is reactants, like that. Label the axis. This is reaction progress on the x-axis, or time. And on the y-axis, we have heat energy. The reactants are, for number 3, it's H2 plus O2, and it's 2H2 plus O2, and the product, 2H2O. We then draw our activation energy, our hump, and we connect it to our products like this. All right, we would label this the activation energy. We call it EA, activation energy. And we will call this the released energy. Okay, that is a reaction profile diagram, knowing that the reactants are higher in energy than the products. So well done if you got that right from memory. Great stuff. All right, guys, that was a long video, but we'll set the groundwork here for some important stuff that's coming up. So well done, and I will see you in the next video.